Welcome to the Deep Dive. And hey, this one's a bit special. It's built just for you, Mr. Martin's grade 8 science class.
That's right. We heard you're getting into energy, a massive topic in science.
Totally. So our mission today, give you the ultimate edge, kind of a shortcut to really getting the essentials. We're talking types of energy, the rules, and this really important idea called efficiency.
Yep, we've looked through your materials, pulled out the key bits. We want to go beyond just memorizing definitions and really understand why energy moves and changes the way it does.
Before we dive in, though, quick reminder for everyone in the class, if you find this helpful, seriously, hit that follow or subscribe button. That way you won't miss future study stuff we put out.
Yeah, definitely do that. Okay, so goals for today. We've got 5 main things we want you to walk away with.
Right? Lay 'em on us.
By the end of this, you should be able to name the different types of energy, describe how it transforms, use the law of conservation of energy. That's a big one.
Yeah, keep going.
Identify useful versus wasted energy, and, crucially, calculate efficiency. Get those down, and you're in great shape.
Perfect. Okay, let's start right at the beginning. Energy. Your sources say it's basically the ability to do work, or like what makes things happen and change. Simple enough, right?
It sounds simple, but yeah, it's fundamental.
Yeah.
And the interesting thing is it's not just one single thing. Energy comes in, well, several different flavors.
Right, 9 types according to your materials. That seems like a lot to remember.
It does, but we can group them. Thinking in categories makes it much easier, maybe 4 main groups.
Okay, I like groups. Group 1, maybe energy about moving or being somewhere. Like kinetic energy, that's movement.
Exactly. Kinetic is motion. And in that same group, let's put gravitational potential energy. That's the energy stored just because something is, high up.
Got it. Anything else in group 1?
Yes, elastic potential energy. Think stretching a rubber band or squashing a spring. That's stored energy. That's elastic potential. So motion and position stuff.
Okay, group 1 done. What's group 2?
Let's call group 2 wave energy. This is energy that travels like ripples on a pond. So sound energy, which is vibrations moving through air or something else.
And light energy too, right? That travels as waves, allows us to see.
Perfect. Light is definitely in there. Group 3 is where things get really powerful. Let's call it stored chemical and nuclear energy.
Okay, chemical energy. That's like in food or
Yeah.
batteries, fuel.
Exactly. Stored in the bonds between atoms and molecules. And then there's nuclear energy, huge amounts of energy stored deep inside the nucleus of an atom. Massive potential there.
Wow. Okay, so that's 3 groups. What's the last one?
Group 4 is kind of the everyday workhorse group. Let's put thermal energy or heat and electrical energy here.
Heat, we feel that all the time. And
Yeah.
electrical energy, moving electric charges, like in wires, powers almost everything.
Pretty much. So that's our 9 types, sorted into 4 easier-to-handle categories. Thinking about them this way helps because, honestly, they rarely stay put.
Ah, okay, so they change. That leads us right into the next big idea, transformation.
Exactly. How does one type become another type? That's the key question.
Like if I eat breakfast chemical energy and then I don't know, ride my bike kinetic energy, what's the rule for that change?
The rule is huge. It's called the law of conservation of energy. Some call it the iron rule of the universe. It's fundamental.
Okay, sounds important. What does it say?
It says energy cannot be created or destroyed, ever. It can only be transformed or, changed from one type into another.
Cannot be created or destroyed. Got it. So what does that actually mean in practice? Like what does it stop from happening?
Well, it means you can't get something for nothing. No perpetual motion machines. The total amount of energy you start with the input must equal the total amount you end up with the output. Always.
Even if some of that output isn't what you wanted.
Especially then. That unwanted energy still has to be accounted for. If your numbers ever show more energy out than in, you've broken physics. The books must balance.
Okay, the books must balance. Let's try applying that. Let's track the energy in something simple like switching on a torch.
Good example. Okay, inside the torch, you've got a battery. That's stored chemical energy.
Right.
When you flip the switch, you close the circuit. That chemical energy starts converting into electrical energy. Electrons start flowing.
Okay, so chemical to electrical. Then what?
That electrical energy flows through the wires to the little bulb. And inside the bulb, that electrical energy transforms again, transferring out into the surroundings as, 2 main things.
Light, obviously. That's what we want from a torch.
Right, light energy, but also heat energy. Torches get warm, don't they?
Yeah, they do. Okay, so chemical to electrical, then electrical splits into light and heat. The total output energy, light plus heat, equals the electrical energy that went in.
Precisely. Let's pause on that battery conversion for a sec.
Sure.
When we say chemical energy converts, are we talking about atoms actually moving around?
Good question. What's happening there?
It's more about the potential energy stored in the arrangement of the atoms, in their chemical bonds. When the chemical reaction happens, the atoms rearrange and that stored potential is released, pushing electrons along. That's the electrical current.
So it's like releasing stored energy to make something move.
Exactly. Stored potential converting to cause movement, which is electrical flow in this case.
Here's another example, rubbing your hands together when it's cold.
Ah, yes.
Yeah.
Classic. You start with chemical energy stored in your muscles, right?
Right.
From food.
Right. Then I use that to move my hands.
Which is kinetic energy. Your hands are moving. Then friction between your hands does the next conversion.
Friction turns the movement into heat energy.
Yeah.
And maybe a tiny bit of sound.
Exactly. Mostly heat. Now, here's a slightly tricky question for you, building on that. If you're rubbing your hands because you're cold, is that heat useful or wasted?
Huh. Okay. Well, I want my hands to be warmer, so useful.
You got it. It depends entirely on the purpose of the action or the device. We call this defining the system boundary. If the system is you warming your hands, heat is useful.
But if it was, say, an electric motor that's just supposed to spin something and it gets hot while doing it,
Then that heat is wasted energy
Mm.
because the motor's job was just to create motion, not heat.
Mhm.
So useful really depends on the intended job.
That distinction is super important, especially for your science classes. Okay, let's tackle that trampoline example your notes mention. It seems like energy changes back and forth there.
The trampoline is perfect for showing potential and kinetic energy swapping. So you're standing high up on it, right? Lots of gravitational potential energy, TPE.
Yep. Then I jump down.
As you fall, that GPE converts into kinetic energy. You speed up,
Then I hit the trampoline mat. Splat.
not splat. Stretch. That kinetic energy gets transferred into the mat, stretching it. That's stored elastic potential energy now.
Ah, okay. Start in the stretched material.
Yeah.
And then,
Then the mat springs back. That stored elastic potential energy converts back into kinetic energy, launching you upwards.
and as I fly up, I slow down. The kinetic energy is changing back into...
Gravitational potential energy again
Yeah.
as you get higher. Now, in a perfect world, with no friction or air resistance,
Which doesn't exist.
right, it doesn't. But if it did, you'd bounce back up to the exact same height you started from. Your GPE at the top would be the same each time. You'd bounce forever.
But we don't bounce forever. We lose energy somewhere.
Exactly. And thinking about what gets lost, or rather changed into forms we don't want, that's our perfect bridge to talking about efficiency. Because real-world systems aren't perfect.
Right. Some energy always seems to go somewhere else. So we need to separate the energy output into two types. Useful and wasted.
Precisely. Useful energy is the output we actually want for the job. Like, for a fan, the useful energy is the kinetic energy of the moving air.
And wasted energy is the stuff we don't want. Like the fan motor getting warm or making noise.
Exactly. Noise is sound energy, warmth is heat energy. If those aren't the intended outputs, they're considered wasted in that context.
Let's use the electric drill example again. I want it to spin. That's useful kinetic energy.
But it also vibrates, makes a racket, and gets hot after a while.
So that vibration, sound, and heat, that's all wasted energy.
Okay.
And your notes had a specific term for what happens to that wasted energy, didn't they?
Yes, a really important one. Dissipated energy. That wasted energy doesn't just vanish, remember the conservation law.
Right. Can't be destroyed.
It just spreads out into the surroundings, dissipates.
Yeah.
Usually as low-level heat, warming up the air or the drill casing or the environment, a tiny, tiny bit.
Okay, so dissipated means it's spread out and sort of lost to the main purpose. Like, imagine you have 10 pounds, that's your input energy, to buy a specific toy.
Okay.
You buy the toy for 7 pounds, that's your useful output. But maybe you also spent 2 pounds on sweets, you didn't really need wasted energy, and 1 pound coin just fell out of your pocket onto the grass somewhere that's dissipated.
That's a great analogy. The money still exists, that 1 pound is still out there, but it's scattered, and you can't easily use it for buying the toy anymore. It's dissipated.
So energy is conserved, but some always gets wasted or dissipated. How do we measure how good a machine is at doing its job without wasting too much?
That's where efficiency comes in. It's literally a measure of how good a device is at transforming input energy into the useful output energy form we want.
Higher efficiency means less waste.
Exactly. A more efficient machine wastes less energy doing its job.
Now, why should you, the grade 8 students listening, actually care about efficiency numbers on, say, a fridge or a washing machine?
Yep.
Besides getting a good grade, I mean.
Well, it hits the wallet.
Mm,
Higher efficiency appliances use less electricity to do the same job. Less electricity used means lower electricity bills for your family. Simple as that.
that makes sense. Saving money is always good.
And thinking bigger picture, if everyone uses more efficient devices, we need to generate less electricity overall. Less generation often means burning less fuel, which means less pollution, less impact on climate change. It's actually a pretty big deal.
Making every joule count. Okay, I get it. So let's get into the math. How do we calculate this efficiency thing? Energy is measured in joules, right? Symbol show.
Correct, joules J. And the formula is your main tool here. It's energy efficiency, useful output energy, total input energy.
Useful output divided by total input. Okay.
And think about it, the useful output can never be more than the total input because energy isn't created. So the answer will always be a number between 0 and 1.
Like 0.8 or 0.3 or something.
Exactly. And to make it more intuitive,
Hmm.
we usually multiply that decimal by 100 to turn it into a percentage, like 80% efficient or 30% efficient.
Right. Percentages make more sense day to day. Now, your notes also mention a way to visualize this. Sankey diagrams. Sounds fancy.
They look a bit fancy, but the idea is simple and super useful. A Sankey diagram is basically a flow chart showing where the energy goes.
Like mapping the money flow in my toy analogy.
Kinda, yeah. The key thing is the width of the arrows. The width represents the amount of energy. A thicker arrow means more joules are flowing down that path.
Okay, so the input arrow is thick, representing 100% of the energy going in.
Usually, yes.
Mm.
Then it splits. A wide arrow branches off, showing the useful energy output, and then narrower arrows branch off, showing the different types of wasted energy.
Like for that drill we talked about, maybe it was 58% efficient.
Right, so the input arrow is 100 units wide, an arrow 58 units wide goes straight, labeled useful kinetic energy. Then maybe another arrow, say 30 units wide, branches off down, labeled heat, and a smaller one, 12 units wide, branches off sideways, labeled sound.
And 58 plus 30 plus 12 equals 100. The widths have to add up. Conservation law again.
Always. The total width out must equal the total width in. It's a visual check.
Cool. Let's try calculating efficiency with some numbers from your materials. Make sure we got this.
Okay, example 1. A simple lamp. Let's say it uses 100 joules of electrical energy as input,
Okay, 100 J in.
and it produces 45 joules of useful light energy. Question: how much energy is wasted as heat, and what's the lamp's efficiency?
All right. Well, if 100 J went in and only 45 J came out as useful light, the rest must be waste. So 100 minus 45, that's 55 joules wasted as heat.
Perfect. Now the efficiency. Use the formula.
Efficiency, useful output, total input. So 45J divided by 100J, that's 0.45.
Yep. And as a percentage.
Multiply by 100. 45% efficient. Wow, less than half the energy is actually useful light.
For older incandescent bulbs, yeah, that was pretty typical. Lots of wasted heat. LEDs are much better now.
Okay, let's try one more, maybe slightly trickier. Your notes mention a motor. Input is 5,000 joules of electrical energy.
5,000 J electrical in.
The useful output is 1,000 joules of kinetic energy, making something spin. What's the efficiency?
Okay, same formula. Efficiency, useful output, total input.
So 1,000 J divided by 5,000 J, let's see, that's 15th, which is 0.2.
Right. And as a percentage.
0.2 times 100, that's only 20% efficient.
Exactly. So that motor wastes 80% of the electrical energy it consumes, probably mostly as heat.
Okay, I see how that works. And a key warning you mentioned. The input energy number should always be the biggest number in these calculations, right?
Absolutely critical. If you ever calculate an efficiency over 100% or find that the useful output is somehow more than the input, stop. You've made a mistake somewhere. Go back and check. The law of conservation won't be broken.
Got it. Input is king. Well, this has been really clarifying, a great deep dive into the mechanics of energy. Let's quickly recap for Mr. Martin's class.
Good idea. We started with the basics, what energy is, and then looked at the 9 types, grouping them to make them easier to handle.
Then we had the big one, the law of conservation of energy. Energy isn't created or destroyed, it just transforms. The total amount stays the same.
Yep. And that led us to distinguishing between the energy output we want useful energy and the energy output we don't want wasted energy, which often gets dissipated, just spreads out.
And finally, we got the tools to measure how good devices are at making useful energy. The efficiency formula, useful output, total input, and those visual Sankey diagrams with the arrow widths.
That covers the core concepts. Now for a final thought to chew on, something that brings us back to, well, biology. Think about a cheetah running.
Okay, fast animal, lots of kinetic energy.
Right. Your source material mentions a cheetah might produce, say, 5,000 joules of useful kinetic energy when sprinting.
That's the useful output.
Now, cheetahs, like most mammals, are actually not super efficient at converting food energy into motion. Let's say a cheetah is about 20% efficient.
Only 20%. Wow, okay.
So the question for you students is, if the cheetah produced 5,000 J of useful kinetic energy and was only 20% efficient, how much chemical energy did it have to get from its food as input?
We need to work backwards. We know efficiency, useful output, total input. So total input, useful output efficiency.
Exactly. Plug in the numbers. Remember to use efficiency as a decimal, 0.20.
So 5,000 J divided by 0.20, that's
Right.
25,000 joules.
25,000 joules of chemical energy input needed from food just to get 5,000 J of useful running energy out.
Whoa. So 20,000 joules were basically wasted as heat.
Largely dissipated as heat, yeah. Keeping the cheetah warm, powering other bodily functions, but not contributing directly to that sprint. It shows that even nature has to obey these energy laws and deal with efficiency limits.
That's a fantastic example. Energy transfers are literally happening inside all of us right now. Okay, that wraps up our deep dive for today. Seriously, huge thanks for sharing your source materials with us, Mr. Martin's Grade 8 class. We really hope this helps cement these ideas for your lessons.
Yeah, absolutely. Study smart. Remember to define useful versus wasted for each situation and keep that conservation law in mind. Good luck.
And one last time, don't forget to hit like or subscribe if this was helpful. We'll catch you on the next deep dive.